Hello and welcome to the Scientific Adventures of Beardman. Today we're going to be looking at the California Science Test Practice Test, the CAST Practice Test, and we'll be going through each question, giving you a chance to note your answer, and then going through what the answer is. So let's go ahead and get into it. First, you get to this page with all these things. I just leave it what it is. You check your sound and video playback. If that's good, you say you can play it, and then you begin test now. All right, and we see our first question. The leaf beetle, Chrysomela anicolus, probably, lives in the Sierra Nevada mountains of California. Scientists studying the beetles found that exposure to high temperatures during the summer, when the eggs are laid and the larvae are developing, causes psychological stress. The impact is on metabolic enzymes and heat shock protein expression. One allele, PGI4, increased in frequency in the beetle population that was exposed to hotter, drier summers in the Sierra Nevada mountains. Complete the sentence about this change by selecting the correct words from the menus. If the temperatures in the Sierra Nevada mountains continue to increase, the frequency of PGI4 allele is expected to, and then you'll choose either increase or decrease, as a result of genetic drift, gene flow, natural selection, or artificial selection. Choose your choices now. Be sure you think carefully about your choice, even if it's briefly, before you go on to look at the answer. After each question, take the time, pause the video, and think about what your choice would be. It's part of the way our brain works. When we think about what our choice would be, then our brain determines that that answer is important. And so when we find out whether we're right or wrong, it knows to store away that piece of information. So take a moment now to actually mark your answer. Now that you've chosen your answer, let's go through the problem, talk about some of the things in here. First, let's look at the word allele. An allele is one of two or more versions of a DNA sequence at a specific genomic location. In other words, your DNA is changing a little bit in one part, okay? Or it's different between different animals of the same species. At different frequencies. And it says that it increases in frequency when there are hotter, drier summers. Okay, so we're seeing a cause and effect here. And then we find if the temperatures continue to increase, based on the only evidence we have, that is when the temperature increases, this allele becomes more frequent, then this allele is expected to increase. There's no evidence that it would do otherwise. Okay, since the only evidence we have is that it increases when it gets hotter. Then the big key is which of these four choices is causing it. Well, let's go through the definitions of each of them. So genetic drift is the change in frequency of an existing gene variant in the population due to random chance. Since this isn't due to random chance, this is because of a cause, the temperature increasing, we can eliminate that one. Gene flow is also called gene migration. Gene flow is the transfer of genetic material from one population to another. Well, since this is still occurring in Chrysomela anicolus and not some other population, some other kind of beetle or something, then this would not be gene flow because it's still within the same population. Natural selection is the process through which populations of living organisms adapt and change. So presumably the reason that this allele is becoming more common is because the alleles, the Chrysomela anicolus that have this PGI4 are better suited to survive in the hotter, drier climates, and therefore naturally it picks out the one that's more likely to survive. So that does seem like the correct answer. But before we select it, let's check all our answers, make sure this one isn't better. It says artificial selection is the identification by humans of desirable traits in plants and animals and the steps taken to enhance and perpetuate those traits in future generations. In other words, if you like the way a particular corn tastes, you try to make sure that corn is repopulated so you get better tasting corn. We're intentionally doing it. There's no indication here that the humans are making the hotter, drier summer. We'll leave climate change aside for now. All right, so that means since nature is causing the selection, that will be natural selection. So now on to question number 2. Students use the periodic table to predict reactions between different elements and elemental bromine, Br2. An incomplete equation for the reaction between an element and Br2 is shown. Bromine atoms have 7 valence electrons. Blank plus Br2 becomes blank. Based on the number of valence electrons of elements in a compound, which is an ionic compound that can form in a reaction between an element and Br2? A. SBr2, composed of S2 plus ions and Br minus ions. B. CaBr2, composed of Ca2 plus ions and Br minus ions. C. Br4, composed of C4 plus ions and Br minus ions. KBr2, composed of K plus ions and B minus ions. Go ahead and choose your answer now. To get our answer for this, we're going to need to look at the periodic table. So I'm going to just write down the elements that we have to possibly bond with the bromine. And remember, this is an ionic bond. So now that we've got those, let's come up here to the periodic table. Let me go back to using my mouse and click on the periodic table. And so here we have the periodic table. We can see that S is right over here. Ca, calcium, is over here. C, carbon, is here. And K, potassium, is here. So the number of valence electrons that each one has, and the problem told us to use the valence electrons. If you're in the first column here, you have 1 valence electron. So potassium in the first column has 1 valence electron. Calcium has 2. Carbon has 4. The 10 are the D level. We won't get into that here. But carbon has 4, and it will pretty much exclusively covalently bond. So we can eliminate carbon because it will not form an ionic bond pretty much at all, ever. Okay, and here we have 6 valence electrons. So since our bromine has 7, bromine is over here, and it wants to form a negative, meaning it wants to get an electron from something, because all atoms want to either get to 8 or 0, which actually gives them 8 in the layer underneath it. And so if bromine wants to get 1, it could get 1 from potassium, because potassium wants to give away 1, become a plus 1. So 1 potassium and 1 bromine would go together nicely. But if you remember, our problem here, whoops, I'm not in mouse mode. So let's get back to mouse mode. Our problem when we had KBr was they put 2 bromines with the potassium, and that wouldn't happen because only one of them would want to go with it. So let's take a look at our other options. So potassium doesn't work because they chose the wrong number. There would only be one of them. Carbon, only covalently bonded. And so we're with S and Ca. Well, S wants to give away 2 so it can get to 0. Okay, so that would make it 2 plus. Sorry, excuse me, that's Ca. Ca wants to give away 2, so it would be 2 plus. Si Let me erase that because that is hard to read. There we go. Okay. So Si or S over here, sulfur, that has 6. It would get to 8 easier than getting to 0. So it wants to gain 2. So it would actually give you a 2 minus option. And we were only given the option of it being S2 plus, which doesn't actually happen. It would be S2 minus. So our correct answer will be Ca, because since the Ca wants to give away 2 electrons, the Ca can give 1 electron to this bromine and 1 electron to this bromine, making both of them Br minus, and the Ca becomes 2 plus like it likes to be. And therefore we get a balanced situation with 2 negative 1s and 1 positive 2 that balances out our charges. So B would be the correct answer here for that reason. And on to question number 3. Students are investigating the relationship between human population density and biodiversity. The amount of forest cover was used as a measure of the biodiversity of an area. The students averaged human population density and forest cover from various locations with a range of population densities. The graph shows the students' results. Here's the graph: forest cover and human population density, with forest cover in percentage on the y-axis and human population density in per square kilometer on the x-axis. Part A. Select a phrase from the menu to complete the sentence. Based on the graph, if the population density increases from 1 to 500 people per square kilometer, the forest cover will likely decrease by about 50%, decrease by about 500 kilometers, or double in size in that area. Go ahead and make your choice now. So to answer this question, we're being asked how the forest cover will change when we change the population density. So how the forest cover will change when we change the population density. So let's go ahead and zoom in on the graph here. We see that the population density is changing from 1 to 500 people. Okay, looks like I lose my pen there. There we go. So if we zoom in here, we're changing from 1, which is essentially 0, to 500 people. So that means we're dealing with this point on the graph and essentially this point. Okay, so we can see that the forest cover when we have 1 person is just under 100. Maybe it's supposed to be at 100. It's a little bit unclear with the thickness of the lines here. And we see this one's just about at 50 or maybe a tiny bit below 50 once we get to 500. So that means when we change from 1 to 500, from 1 to 500, that means we change from about 100% forest cover to about 50% forest cover. All right, so based on that, decrease by about 50% sounds right because we were at 100 and we went down to 50%. Just to point it out, it says decrease by 500 kilometers. Forest cover isn't measured in units of kilometers, so that would kind of eliminate that one. Double in size would mean gets bigger, and clearly the forest cover is getting smaller, going from nearly 100 to nearly 50. So decrease by 50% is the answer to part A. Moving on to part B of number 3, we see that the students identified 4 resource management strategies intended to help preserve forest cover and maintain biodiversity. The students then ran computer simulations to graphically compare the different resource management strategies. Which graph shows results for a resource management strategy that will best preserve forest cover as population density increases? And you can see there are 4 graphs down here with different curves for how the forest cover responded to human population density. Okay, so we can see 4 graphs there. Go ahead and make your choice now. Now that you've had time to make your choice, let's talk about the answers. So I think the obvious one, if we look at this, first of all, we see that this is where the forest cover started with 0 population based on the model they're using, and it decreased to 20% by the end. It is curved a little bit more generously in this part of the population density change compared to the one up here, which decreased really quickly at the beginning. So it does help it in the initial stages, but it gets worse and worse as you get bigger. And so if you were to go beyond 2000, it seems like it would be the worst, even worse than just letting things go as they are. This one looks really good. This is probably going to be our choice. It starts at 100% forest cover, and it goes all the way up to 2000 with only a decrease of 20% of the forest cover, leaving 80% of the forest cover, as opposed to having 80% of the forest cover destroyed. So that's really good. Here we have an interesting choice. Apparently, they're chopping down half the forest cover to begin with. So we start with about 50%. The one thing about this, though, is it does level out here. So you looks like the trend is going, if we were to get more than 2000, it looks like it would just stay at 20% forest cover, which could be good compared to the other ones. If we're going to get to places like Singapore that have 18,000 people per square kilometer. In this final one, we see that it dips down to 10%. Again, it does level off. Of course, this one levels off at 10%. This one levels off at 20%. So presumably this one would be better. But there's no indication in the problem of population densities increasing above 2000. And there are very few countries that do increase beyond 2000. Except for city-states like Singapore and Monaco and such places. And so if this is a countrywide phenomena, and based on just the evidence here, we see this one only drops to 80. So I would choose B for the answer to this, which is indeed what the state published as the answer to that. All right, moving on to question number 4. I notice there's a line reader. Let's try and use that. So the reaction A2, which is gas, plus A2B, which is also a gas, becomes or turns into or yields 2A2B, which is also a gas, is carried out in a closed 1-liter container. The diagram shows the relative amounts of A2 and AB used for the reaction. We can see here we got 3, 4 A2s and 1, 2, 3, 4, 5, 6, 7, 8 ABs. Assume the reaction is complete. Drag the correct number of molecules of A2B that will be produced to the empty box. So you're going to choose one of these boxes here and drag it up into the box. So go ahead and make your choice. We'll call this 1 or A, 2, 3, 4, 5, A, B, C, D, E, depending on what multiple choice you've been given. Make your choice now. So the key thing here is conservation of matter. Since we start with 1, 2, 3, 4, 5, 6, 7, 8 of the B atoms, and 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of the A atoms, none of those atoms can disappear. They can only rearrange. So we have to pick one that has 8 B's and 16 A's. This only has 2 B's and 4 A's, and so on up the line until we get to our far right one here that has 1, 2, 3, 4, 5, 6, 7, 8 B's, and each one has 2 A's. That's 16 A's. So that would be your correct answer. So let's head on to question number 5. So here we see students noticed that a nearby pond, fed by a stream, was filling up with sediment. The students want to determine what factors are contributing to the amount and type of sediment entering the pond. Which investigation is most likely to produce data that will help answer their questions? A. Measure the depth of the sediment in the center of the pond once a week during the school year. B. Collect and measure the mass of particles carried by the stream in 1 minute and then in 10 minutes. C. Collect and measure the mass of clay particles, silt particles, sand grains, and small pebbles carried by the stream at different stream flow velocities. D. Obtain samples from different depths in the sediments at the bottom of the pond and determine how the sizes and amounts of particles have changed over time. Go ahead and mark your answer now. So if we look at the question up here, we can see that we're trying to find or determine what factors are contributing to the amount and type of sediment entering the pond. Okay, so the factors, what's happening with the river or stream that's contributing to the amount and type of the sediment. So in A, we see it measure the depth of the sediment in the center of the pond. We don't see anything about what factors, nothing about what factors are going on here. So it can't be A. B, collect and measure the mass of particles. So at least we're getting now the type of particles, because the type of sediment is separated by mass of the particles. Or size of the particles at least, carried by the stream in 1 minute and 10 minutes. So we see time, but we don't see any factors contributing to the amount of the particles. So then we see collect and measure the mass of clay, silt, sand grains, and small pebbles. So now we've got our type of sediment carried by the stream at different stream flow velocities. So that's a different factor. How fast is the stream flowing is a factor there. Okay. And so this does seem to be correct. Let's read the last one. Obtain samples from different depths in the sediment at the bottom of the pond and determine how the sizes and amounts of particles have changed over time. Well, if we had some other data that let us know what factors were present at various times, then perhaps we could have chosen this one, but there's no indication of that. And so if all we do is know the times, that doesn't help us know what factors contributed to the amount and type of sediment. So therefore C is the best answer we can choose. All right, let's head on to question number 6. So here we see that a biochemist conducted an experiment to follow the movement of glucose molecules in animal cells. Glucose, with radioactively labeled carbon atoms, was added to a culture of liver cells growing in a petri dish. Over the next 18 hours, the biochemist assessed selected biomolecules in the culture for radioactivity. The results are shown in the table. We can see the table here, presence of radioactive carbon, and it shows us every 3 hours, right in here, every 3 hours, whether glucose was present, or whether glucose had the marked atoms, and whether the glycogen had the marked molecules. Explain how adding labeled glucose molecules to the culture resulted in labeled glycogen, and describe what happened to the labeled glucose molecules during the 18-hour period. Enter your answer in the box provided. Go ahead and type your answer in now. So it's important as you're working on this to notice the no's. The no's are really important. Okay, so we started out with glucose with the markings, but no glycogen. And so you definitely need to mention that the glucose is incorporated into or stored in the glycogen. So we can see it's here, and then all of a sudden that glucose that wasn't part of the glycogen now is. And so we can see that that's being stored or incorporated into the glycogen. And also within the first 6 hours, by the time we get to 6 hours here, it's been stored there. And by the time we get to 18 hours or even 15 hours, we can see that the glucose was all used up for energy or stored in the glycogen. All right, so let's head on to question number 7. Here we see that a student is learning about the life cycles of low mass and high mass stars and creates a chart comparing the properties of the stars. Complete the chart by placing a check mark in the box or boxes in each row to indicate if the property applies to low mass stars, high mass stars, or both. Has a higher core temperature during main sequence stage. Spends a longer time on the main sequence. Burns hydrogen at a faster rate during main sequence stage. Spends the majority of its lifetime burning hydrogen in its core. Can create elements heavier than iron during supernova event. All right, now that you've recorded your answers, let's talk through these one at a time. So, has a higher core temperature during its main sequence stage. Well, low mass stars have less gravity pulling them together, so they aren't as hot in their core. High mass stars have more pulling them together, and as gas is compact, they heat up. So that would be a high mass star. Spends a longer time on the main sequence. Well, although high mass stars have more material that they can burn through, low mass stars are at such a lower temperature that the rate at which they're burning them is a lot slower. I like to compare it to a big car like a Suburban or some big heavy thing. It might have a bigger gas tank, but it's going to burn through its fuel faster. Whereas the Prius, even though it's got a smaller gas tank, will be able to go farther because it burns less with each gallon or with each mile. Stars are the same way. Then burns hydrogen at a faster rate during its main sequence stage. Well, because they're higher temperature, that means that their fusion is enabled at a greater rate. And so you will have high mass stars burning through their hydrogen at a faster rate. Burning isn't quite the right word. Fusing would be a better word there. Spends the majority of their lifetime burning hydrogen in its core. Well, the only other time that's considered part of their life is when they're fusing helium into carbon, into magnesium, and so forth, up to iron. And that period, the red giant phase, happens very quickly compared to the rest of the phase. So that would actually be both of them. Even though high mass stars have a quick main sequence phase, they have an even quicker red giant phase. So the majority of their life is burning hydrogen in their core. Then our final one can create elements heavier than iron during a supernova event. Small mass stars don't have enough energy to undergo a supernova event. So they cannot make something bigger than iron. It must be a high mass star in order to go through the supernova event, which then results in a neutron star or a black hole. All right, let's head on to question number 8. Laser light of wavelength 785 nanometers is in air, travels from air, index of refraction equal to 1, into a glass block, index of refraction equal to 1.5. The frequency of the light does not change when the light enters the glass. How does the wavelength of the light change, if at all, when the light enters the glass? And what reasoning supports this claim? The wavelength stays the same because the wavelength can only change if the frequency changes. The wavelength stays the same because the speed of light is constant and the frequency does not change. The wavelength decreases because the speed of light in the glass is less than the speed of light in air and the frequency does not change. And finally, the wavelength decreases because the speed of light in the glass is greater than the speed of light in air, and if the speed increases, the wavelength must decrease. Go ahead and put your answer now. Right. In order to figure out this question, we're first going to have to make sure we recognize that we are entering glass, and we need to know that light slows down when it enters a medium other than a vacuum. The explanation for this gets quite complex, so I'm not going to get into it. There's even some disagreement among top people exactly how to think of it. Um, but the basic idea is that the electromagnetic waves, the light, cause the protons and electrons inside the material to move around, and moving charges create electric and magnetic fields of their own, and that interferes with them somehow and slows them down. So every substance has a certain amount that it slows down, but moving from a vacuum, we know that it's going to be slower in the glass. The second part of this is we look at our formula sheet. Up here's where our little formula button is, right up here, and that opens up this sheet. We can see that v, the speed of light, is equal, or speed of a wave, is equal to the frequency of the wave times the wavelength. So in our particular example, we have the fact that the frequency is not changing. Okay, we could get into that in a different video, why that is, but this problem just tells you that. So that means if the velocity is getting smaller and the frequency didn't get smaller, that meant the wavelength had to get smaller. Okay, and if we look down here, we can see that the one that says the wavelength decreases because of the speed of light in the glass is less than the speed of light in the air, and the frequency does not change. That would describe what we were just talking about. All right, let's head on to question number 9. In a particular species of plant, yellow seed color is dominant to green seed color. Two plants of this species that are heterozygous for seed color are crossed. What is the predicted ratio for seed color in the offspring of this cross? A, 1 yellow to 3 green. B, 1 yellow to 1 green. C, 3 yellow to 1 green. D, 3 yellow to 2 green. To solve this problem, we'll need to use a Punnett square. So that's when you have genes like this, if they are heterozygous, as we see here, that means that each seed will have a yellow gene and a green gene, one of each, hetero, different. I made the Y capital because yellow was dominant and green was not dominant, recessive. And so we make the square by making a little four square thing here. We say one parent had a yellow and a green gene, and the other parent had a yellow and a green gene. Then we just follow from each box. This one has a yellow and a yellow. This one has a yellow and a green. This one has a yellow and a green. And this one has 2 greens. Well, since yellow is dominant, that means all of these will look yellow, will have a yellow color, and only this one will have a green color. So that is a 1 green to 3 yellow ratio. So here we see 3 yellow to 1 green. So C would be our correct answer. And let's head on over to question number 10. This diagram shows the boundary between the Indian plate, you can see the Indian plate here on the left, and the Eurasian plate here on the right. Select the best terms from the menu to complete the following statements. The mountains were formed as a result of the Indian plate colliding with, or diverging from, or sliding over the Eurasian plate. Over time, the effects of weathering and erosion, or strike-slip faults, or sedimentation will counteract the process that builds the mountains? Go ahead and answer those questions now. All right, as we look at the choices here, we can see that these are either colliding, diverging, or sliding over. Uh, Diverging, first of all, means moving apart. And we can see the Eurasian plate is moving to the left and the Indian plate is moving to the right. They're moving towards each other. So that's definitely not diverging. So sliding over and colliding are the two where they are moving towards each other. Sliding over typically happens when you have an oceanic plate that's heavier and more dense sliding under a continental plate. But since they're both continental plates here, they're just going to flat out collide. And that's what's going to form these mountains. As it's mentioned here, the mountains were formed because they're colliding. Then over time, the effects of, so we want to think of something that's going to be the opposite of building up the mountains. Strike slip faults deal with situations where things are sliding past each other, so that's not going to wear away the mountain. Sedimentation is when little bits of sand and rock end up somewhere and they build up the land there, not break it down. Weathering and erosion. Weathering is the breaking apart of rocks, and erosion is the process of that being moved somewhere else, pretty much always downhill. Often through rivers and streams, but sometimes by the wind. So weathering and erosion is going to counteract the process that builds the mountains. Right, let's head on to question number 11. A student performs an experiment in which a cart is pulled across the table by exerting a net force of 0.05 newtons on the cart. Different amounts of mass are added to the cart for each trial. The graph shows data from the experiment. And we see here we have mass versus acceleration. We have acceleration on the y-axis and the mass of the cart on the x-axis. Based on the results from the experiment, what claim can the students make about the relationship between net force, acceleration, and mass? A. Objects with a smaller mass experience a larger acceleration and therefore a larger net force. B. Objects with a larger mass experience a smaller acceleration and therefore a smaller net force. C. Objects with larger mass experience a smaller acceleration when the net force is the same. And D. Objects with smaller mass experience a smaller acceleration when the net force is the same. Choose your answer now. The first thing to notice here is that two of these have the net force changing and two of them have the net force staying the same. Well, let's take a look at the problem. It says that we're doing this experiment by always exerting a net force of 0.05 newtons. So every single one of these trials had the exact same net force. So based on this experiment, we're going to be talking about things where the net force is the same. So that eliminates A and B. Then we just have to look at our graph here and see that when we have a small mass, we get a large acceleration. And when we have a large mass, we get a small acceleration. So that would be describing the situation where objects with a larger mass experience a smaller acceleration when the net force is the same. 12. Students are discussing a model of a system that consists of two parallel conducting plates called a capacitor, separated by a distance of d, and a positively charged sphere directly in the middle of the two plates. The upper plate has a positive charge, and the lower plate has a negative charge. Upper plate, lower plate, positive charge. In which direction should the charged sphere move to increase the energy stored in the system? To the left with an external force is A. B, to the right with an external force. C, toward the positive plate with an external force. D, toward the negative plate with an external force. Go ahead and answer the question now. So there are two things we have to remember here. First, we have to remember what direction this is going to get pulled. Well, we know opposite charges attract and like charges repel. So this positive charge is going to be pulled this way. So then the question is, do we push the same way it's being pulled, or do we push the opposite? Well, to remember that, most of you have a pretty good understanding of gravitational potential energy and the idea that if we lift up against the pull of gravity, in other words, we make it higher, then it will increase its potential energy. Well, the same thing here for charges. When we pull it against the direction it's naturally being pulled, then that's going to give it more energy. So if we want to give more energy to this positive charge, we have to push it the opposite direction that the electric field is charging it. That would be C, toward the positive plate with an external force. Thank you for watching Scientific Adventures of Beard Man. This is where I'm going to pause this video. I've decided to break the 48 questions into 4 videos with 12 questions each to make them more manageable in one class period. See the playlist for the remaining 3 videos. If you liked this video and you learned something about the California Science Test, please click the like and subscribe button, and we'll catch you the next time on the Scientific Adventures of Beard Man.